Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to introduce the idea of addresses and pointers. So, in this topic, we are going to review the concept of an address. Then we'll consider how to store them. We'll look at some examples and some naming conventions, and then we'll try to understand the size of an address. Now, recall previously that we've discussed the fact that memory is byte addressable. What that means is that every byte has its own unique separate address. For example, if you had 1 megabyte of memory, you would have 1,048,576 unique different addresses. It's convenient to represent these addresses using hexadecimal numbers. Now, the size of an address is fixed for a very specific type of processor that you're currently using. Now, today, most general processors that you see in your laptops or desktop computers or even tablets have 64-bit addresses. That means you can store up to 2 to the 64 different addresses. Older processors and microcontrollers today generally have up to 32-bit addresses. So this means you can store approximately 4 billion different addresses. On the other hand, the PIC 10F200 microcontroller has 8-bit addresses. That allows you to store 2 to the 8 different, or basically it allows memory you to access 256 different addresses. Now, the PIC, the 10F200, costs less than 50 cents. Now, you will recall that integer data types store different numbers of bits. So an unsigned car, why unsigned? Well, addresses probably should start at 0, and we probably don't really require negative addresses. So an unsigned car stores 8 bits, short 16, unsigned int 32, unsigned long is 64, unless you're on a Microsoft compiler, in which case it's 32, in which case you have to use an unsigned long, but that's an aside. All right. Now, notice these numbers. Could we not just use these data types to store an address? After all, the 10F200 has 8-bit addresses. The Intel 486 and most microcontrollers today have 32-bit addresses, and most laptop and desktop computers today have 64-bit addresses. So yes, it makes sense that we could store an address in one of these data types. So for example, wouldn't it be nice if there was a primitive data type with a name like address_t? So here we have a program. We have a local array of type int that stores 10 objects. Now, the variable array actually stores the address of the first byte of the first entry of that array. So it is already storing an address. Wouldn't it be nice if we could declare address of array to store an appropriate address size and then initialize that local variable with an address such as array? In which case, if we printed out either array or the address of the array, these two values should be identical. That would be nice. However, there is no such universal address type in C++. All right, there is a problem here, however, because Yes, we may actually have an address, but what is there? Is what is at that address, is it storing an int, or is it perhaps storing a double or a float? So for example, here, address underscore A would be storing the address of the first entry of an array of type int. Address B would be storing the address of the first entry of an array of type double. So if we just had a generic address type, then the compiler would not know what to do with array underscore A or array underscore B, other than the fact that it knows that those are addresses. Now, C++ does have a solution to this. A variable, be it a local variable or a parameter, can be declared to be the address of an integer or the address of a double, whatever type, by prefixing an asterisk to the identifier. Let's see how this is done. Here we have address underscore A. Address underscore A is the name of the variable. That variable stores the address of an int. In this case, the asterisk is actually a unary operator. Just like the not operator, which appears before the identifier, here the star appears before the identifier, in this case indicating that address underscore A is a local variable that is storing an address, in this case of type int. Here, address underscore B is declared to be the address of a double. In this case, address underscore B is being initialized, or its initial value is the address of the array underscore B. All right, we already know that an array, the name or the identifier of an array, stores the address of the first byte of that array. Well, how about local variables and parameters? After all, they too must be stored somewhere in main memory. So therefore they must have an address. And of course, by address we mean the address of the first byte of that parameter or local variable. The question is, how do we access those addresses? Well, in C++ there is the Unary Ampersand operator that returns or evaluates the address of its one operand. So, for example, the parameter n is of type int, and we can print out its address by prefixing the parameter identifier with the ampersand. So the ampersand there does not access the value of the parameter, but rather it accesses the address of that parameter. And you can think of ampersand address. Next, we have a local variable A of type double. But again, when we print out the address or prefix the name or identifier A with the ampersand, this indicates that this should actually print out the address of A. B, on the other hand, is already an array, so when we print out B, then we get the address at which that array is stored. Alright, so if we were to execute this function, the output may look something like this. So the parameter n is stored at that particular address, the local variable A is stored somewhere else, and the local array is stored at yet another location. just like we can print addresses to the screen, we can store addresses in local variables. So for example, here the identifier p_n is declared to store the address of an integer. It is being initialized with the address of the parameter n. However, just like all other identifiers, if we want to access that address stored at p_n, all we need to do is refer to that identifier explicitly without anything else. So p_n will print the address that is stored there, which in this case happens to be the address of the parameter n. If we were to execute this function in a program, we would get the following output, assuming that this is where these parameters, local variables, or local arrays are currently being stored. Now, a variable, be it a parameter or local variable, that stores an address is referred to in industry as a pointer. So suppose you see that p_var is being declared to be the address of a double. In that case, you may either describe the identifier p_var as a variable that stores the address of a double, or you could be a little bit more succinct. It is a pointer to a double. Why is it a pointer? Because it is the address that indicates where that information is being stored. Now, to be absolutely clear to all readers of your code, it's very useful to prefix the identifier of any pointer with p_. This is not required. It doesn't actually do anything. It is simply a naming convention. But this is a naming convention that is widely used in industry, and it makes it clear to the reader that a variable is specifically storing an address and not, for example, an integer or a double. We will be using this naming convention throughout this course. Now, the compiler will always make sure that all addresses are of the appropriate size for the processor on which the code is to be executed. So you don't have to worry about this. But you may ask, how many bytes is an address on this particular processor? Well, the solution is quite easy. Just print out size of and then specify the type you'd like to find out. In this case, we'd like to find out the size of an address storing an integer. Well, it doesn't really matter whether or not you pick int, bool, double, or short, because all addresses are the same size. Now, on the computer ECE Ubuntu, we get an output of 8 bytes indicating that ECE Ubuntu is a 64-bit computer. That means that all addresses are 64 bits long. It's unlikely any of you will ever get anything else. Well, that is unless you have access to your parents' or your grandparents' laptop or desktop from decades ago. Now, suppose you have an identifier such as p_datum that is declared to be a pointer to an integer. And in this case, it is initialized with the address of a local variable or parameter n that is necessarily storing an int. For example, here is one such program. The local variable n is initialized with the value 42. p_datum is a pointer to an integer and it's initialized with the address of n. We can print out that address. Question: how do we access the integer that is stored at that address? Well, what we do is we prefix the identifier with an asterisk. All right, let's see how that's done. All right, so we've added some code to this program. Now, Here, when we printed p underscore datum, that is going to print the address of the local variable n. This, however, says print what is at the address of p underscore datum. So star p underscore datum actually prints out what is at that address, which in this case happens to be the value 42, because p underscore datum is storing the address of n. However, now I can tell the compiler to issue an instruction to assign to what is at that address the value 100. This does not change the identifier p underscore datum, but rather it says what is at that address assigned to it the value 100. And of course, since p underscore datum is storing the address of n, star p underscore datum assigned the value 100 is the same as assigning the local variable n the value 100. So now, if we were to print star p underscore datum, or whatever is at that address, that's going to be the same as printing the local variable n. All right, so here is the potential output. We have the address stored at p underscore datum. We have what is at that address. After having assigned to what is at that address the value 100, then we see that both star p underscore datum and n have the same value. Not only that, suppose we now change the value of n. Well, guess what? What's at the address of p underscore datum has also changed. Okay, nice. So why do we have to store addresses? Well, we don't really have to store addresses. After all, programming languages like Java do not require pointers. In fact, they specifically did not include pointers in Java because pointers are such a significant source of error. However, in C++, recall that arrays are fixed in their size. What happens if you want to change the size of an array once it's been allocated? Or, local variables and parameters are out of scope as soon as a function returns. What happens if we require memory that continues to exist outside the scope of any one given function? The solution to both of these problems is that we're going to ask the operating system to give us additional memory. But how is it going to pass that memory back to us? It's going to pass back the address, and we are going to store that address, and we will access the memory at that address. Now, we have a plethora of different types of declarations, and the question is, can we make sense of these declarations? That is there something in common? After all, in each of these four cases, what we are doing is we are telling the compiler that this identifier, or these identifiers, mean something. In the first case, it's a local variable n. In the second, it's a local array. In the third, it is a local variable that is storing a pointer to an integer. And the last one is the declaration of a function. Well, basically, for this first one, to either access or store an integer value, you simply use the identifier n. For the array, to access or store an integer, you must use the identifier array, but you need square brackets after it with some sort of integer value. For p underscore datum, Now, up until now, we've been speaking about addresses, and we've indicated that an address has a fixed size based on the processor. Up until now, we've been indexing into arrays with int. So here we have a character array of capacity 100, and we are stepping through the array, setting each entry to the null character. The problem is, on a 64-bit computer, if we had enough memory, we could actually declare an array to have a capacity of 10 billion. So if we wanted to set every single entry of this array to 0, or the null character, then we would have the following for loop. There's a small problem here. The maximum int is 2 to the 32 minus 1, or approximately 4 billion. So all of a sudden, we cannot index into this array with the type unsigned int. We would actually require type unsigned long, or if you're using the Microsoft compiler, unsized long. Now, this may seem problematic. After all, now we have to choose the data type for any index into an array based on the processor. So if we're actually dealing with an 8-bit processor, then we could actually get away with using an index into an array of type unsigned char, 256. For 32-bit processors, we could use unsigned int, but for a 64-bit processor, we should be using unsigned long. Fortunately, there is a universal solution. The standard library has a type, standard size underscore t, that is always guaranteed to be an unsigned integer that can store the maximum index for a particular processor. So from now on in this course, if the purpose of a local variable is specifically to index into an array, it will be declared to be of type standard size t. Now, the next few times that we use this, we'll reiterate this. However, over time, you should get used to having for loops where the looping variable, if it is indexing into an array, to have the type standard size t. From this lesson, you now understand the concept of addresses and how to store information there. You know how to access the address and find the address of, say, a local variable by using the Ampersand Unary operator. You also know how to access and manipulate data that is at a memory location by using the Unary star operator, or the asterisk. You understand the sizes of addresses are different for different computer architectures, and this is dealt with by the compiler. Finally, you know about standard size t. Here are the references, colophon, and a disclaimer. Cheers!